The fifth lecture video on rotational motion will cover rotational power. If you remember from a previous chapter where we discussed power, power is equal to the work divided by the time. This is true in the linear or straight line system. Now we are going to take a look at rotational system power. Rotational power is equal to the torque times the angular displacement divided by time. Another way we can think of this is that power is equal to the torque times the angular velocity, since angular velocity is simply angular displacement divided by time. We can use the letter capital P to represent power, the Greek tau to represent torque, and the Greek omega to represent angular velocity. In this equation, the angular velocity must be in radians per second in the metric system. We will take a look at rotational power in the English system later, as there are a few differences in the equation to make the units work out. Let's take a look at an example rotational power calculation in the metric system. How many watts of power are developed by a racing engine using 455 Newton meters of torque at a rate of 1,610 radians per second? How many kilowatts of power is this? First, we will write down all of the information we were given. The torque tau is 455 Newton meters. The angular velocity omega is 1,610 radians per second, and we are trying to calculate the power P. The basic equation is that power is equal to the torque times the angular velocity. Since this is already written in terms of P, this is also our working equation. The next step is to substitute in our data. Power is equal to 455 Newton meters times 1,610 radians per second. This gives us power of 733,000 Newton meters per second, or watts. We also want to know how many kilowatts of power this is, so this part is simply a unit conversion. We can take 733,000 watts and write it as a fraction over 1, and then multiply by the conversion factor. 1 kilowatt is equal to 1,000 watts. Crossing off the units, the watts, in the numerator and the denominator, we see we are left with 733 kilowatts of power. This concludes our first part of our discussion on rotational power.